What is quantum mechanics? Well, it's basically the study of the smaller world that we do not see that makes up everything around us, including ourselves. This theory intended to apply to everything in the universe, but really manifests and becomes necessary when we look at the minuscule building blocks of our cosmos. Quantum mechanics is necessary to understand simple things such as why the sun shines, or how transistors work, or even why pencils are solid. To get a better understanding of how quantum mechanics work, you need to understand how wave functions work. Wave functions were first discovered along with the first diagram of the atom back in 1909. There's a nucleus in the middle of the proton and a neutron-filled atom, accompanied by electrons orbiting around the atom. Classical Newtonian mechanics stood against this imagery. It claimed that orbiting electrons would be consistently losing energy due to their electromagnetic wave emission, and thus would eventually spiral into the atom's nucleus, rather than continuing to orbit it. If this were true, then all matter would be extremely unstable, and this prediction does not fit the data. Eventually, we came to the conclusion that the electron is not a point particle in orbit, but instead more of a wave, and thus the wave function idea was created. After a while, Erwin Schrödinger composed an equation for how electron wave functions are actually behaving. This equation states that any one wave can be deconstructed into different energy parts, and every energy part evolves at a separate rate. But when we look closely at a charged particle that emits electrons and alpha particles, we are still able to view them as particles instead of waves. And this question as to why we can only see the particles and not waves has still not been answered. Scientists have tried to come up with an explanation, and one explanation suggests that when you are not looking at the particles, they are not obeying the Schrödinger equation. But when you do look at them and make a measurement, its wave function subtly and unpredictably changes. And this was called the Copenhagen interpretation of quantum mechanics. But this theory has a lot of issues that have been brought to light as the years go by. One physicist named Everett did not agree with the Copenhagen interpretation. He disagreed with the fact that their interpretation was adding unnecessary extra rules to the Schrödinger equation and leaving out many unanswered questions. Everett believed that the wave function represents reality entirely and exactly. He also thought that the wave function never collapses. They always obey the Schrödinger equation. One way to compare both interpretations is by a single experiment called Schrödinger's cat. Basically, you put a cat in a box, close the box, and in the box there is an atom that has a 50% chance of either decaying or not. And once this atom decays, a gas is released which would instantly kill the cat. Now there's a 50-50 chance of this happening. So when you open the box, you are either to find the cat dead or alive. So, according to the Copenhagen interpretation, the cat is in a superposition of being dead and alive. And when you open the box, the wave function collapses and the cat is revealed to be either dead or alive. And this happens because you made a measurement. This surely isn't believable, which was Everett's point. The flaw in the Copenhagen version is that the observer is treated as classical. Now, Everett says, ignore all this business about wave functions collapsing. Just obey the Schrödinger equation. There's no collapse, and there's only one wave function, and the observer is quantum in their own right. This is Hugh Everett's way of explaining this. In short terms, measurement is just obeying the laws of physics, by opening the box and seeing what is inside. And once this is done, the wave function of the universe evolves to a superposition of the cat being alive and the observer seeing the cat alive, and the observer opening the box to see the cat dead. If the Schrödinger equation was followed, that's exactly what would happen. But it looks like the observer as well would be in a superposition, having seen two different things. But no person has ever felt that they are in a superposition. The immediate rejection of Everett's theory was because it doesn't fit the data. It doesn't explain our experience. This would rather be explained by decoherence, which means an environmental entanglement branches the state into separate components. When conducting this experiment, you can not only consider the cat and the observer, but you also have to consider the environment, even the whole universe, since it's all part of the same wave function. For example, long before the box was opened, in the box there are photons and air molecules. They will interact with the cat, and they will interact differently whether the cat is dead or alive. So a photon may or may not hit the cat depending on whether it's laying down or standing up. The environment becomes entangled with the cat long before you open the box. Then you open the box and create a measurement. But really, you yourself are just becoming entangled with the two different quantum states that were always there. This matters because the environment is doing two different things in two parts of the wave function. The part where the cat is alive and the part where the cat is dead. And what this means is that the separate two terms in this equation evolve separately. They obey their own equations of motion. If something happens in one part of the sum of two terms, it does not affect anything happening in the other term. So, Everett says, this is the prediction of Schrödinger's equation, and it's right. But what people don't understand is, why do you not feel as if you're in a superposition? And the answer is, there are now two of you. There is one of you that saw the cat alive, and there's one of you that saw the cat dead. It's as if these two different parts of the experiment describe different worlds.